another speaker for the day from Swin1.
Hi, Nissa.
Hi, Professor Sriram. Nice
How are you?
To meet
so you are based in Australia?
Yes, I am.
Which place in Australia?
I'm located in Melbourne, Victoria.
Okay. Which one? RMIT or Melbourne University?
Swinburne University of Technology.
Which one?
Swinburne University of Technology.
Yeah. With whom are you working with? Are you
I'm working with. I was working with Professor Bronwyn Fox. She is currently, promoted as the DVCR of the university. So I'm currently, So that's a big news, and I'm currently on a fellowship. So I'm pretty much my own now.
Oh, very good. So what fellowship is this one?
It's a VC, Vice Chancellor's Fellowship.
Oh, okay. Congratulations. You are a VC of the university now.
Oh, yeah. That's what my colleagues say.
I will also say, so, no problem.
Live streaming has started.
Oh, sorry. Okay.
Yeah. Welcome to this second webinar of Carbon Lab 10th anniversary celebration. So we have recently completed our 10 years in IIT Hyderabad, and it's our great pleasure to have today with us Professor Sriram Ramakrishna from NUS and Dr. Nissa Saleem from Swinburne University of Technology, Australia. So as we know that on the occasion of 10th year celebration, we have started this webinar series. First webinar was arranged on 20th December in the field of energy storage devices and carbon nanomaterials. And this is the second webinar in the series on nanofibers. So as I mentioned, today we have our distinguished speakers. And before we go to the talks today, we have a small presentation on the Carbon Lab contribution in the area of nanofibers. So let me just play that presentation. So let me share the screen. So with this brief introduction of Carbon Lab, I now hand over the proceeding to my students, Akansha and Poonam, to proceed further.
Thank you so much, sir. A very warm and pleasant morning to one and all. I am Poonam Rani with my colleague Akanksha Rohila. We are PhD scholars at Carbon Laboratory, IIT Hyderabad. We would like to welcome all the viewers in the second webinar of the series titled Nanofiber, observing 10 years of success of our Carbon Lab. Before we start with our esteemed speakers today, I would like to request Dr. Mrinalini Gaidhane, postdoctoral fellow in Carbon Laboratory, to summarize Carbon Lab contribution in the area of nanofibers. We request you all to post your questions in YouTube chat box. We will take them up at the end of the webinar. Welcome, Dr. Mrinalini.
Thank you everyone for joining us in 10th year anniversary celebration of Carbon Lab. I take this privilege to present research on electrospun, polymer and carbon nanofibers, contributions of Carbon Lab. I shall discuss the key outcomes from the research work done by Dr. Akash Nathani in sensors, Akanksha Rohila in tissue engineering, then by Sheetal Yadav, Dr. Mani Pujita Illa and myself in healthcare. Before moving into the topic, let me tell you how we fabricate the nanofibers. We use a simple, easily programmable and scalable technique called electrospinning, which utilizes electric force to draw micro or nanofibers from polymer-based solution. As you can see in the video, a basic setup consists of a syringe pump, a voltage supply, and a grounded collector. The polymer-based solution is loaded into the syringe and pushed at definite flow rate. The droplet oozes out from the blunt needle, and after applying an electric field, the droplet gets charged. Now, three different forces interplay at the verge of needle tip. Surface tension and viscoelastic forces act inwardly, tending the drop to be spherical in shape, while Coulombic forces act outwardly, stretching the drop into conical shape, termed as Taylor cone. When Coulombic forces exceeds the other two, a polymer jet with a like charges erupts and travel to the oppositely charged collector. While traveling towards the collector, solvent gets evaporated and dried nanofibers in the form of continuous non-woven matrix are deposited on collector. These nanofibers possess high specific surface area, high porosity, interconnectivity of fibers, and facilitates surface functionalization and easy encapsulation of active molecules such as drugs. In Carbon Lab, we have explored the applicability of electrospun nanofibers in various sectors. In healthcare, we introduced nanofibers for feminine hygiene and as a drug excipients. Considering the cell adhesive mechanism, we fabricated aligned and patterned nanofibers for bone regeneration and further eyelid cell encapsulation for diabetic cure. In agriculture, for the first time, we introduced seed storage bags of nanofibers. Then, amine functionalized nanofibers for fluoride adsorption in polluted water for environmental remediation. In sensors, we developed highly porous as well as hierarchical micro nanostructures as biosensors and gas sensors. And in energy field, we explored carbon nanofibers as an anode material. Today, I shall discuss some of the notable contributions from our lab. First, in healthcare, high absorbency cellulose acetate nanofibers for feminine hygiene application. In commercial sanitary napkins, superabsorbent polymers are added in the absorbent core in order to improve their absorption capacity. However, these superabsorbents are found to have certain adverse effects on the health of user and also on the environment. Here, we demonstrate the potential use of electrospun cellulose acetate nanofibers as a material for adsorbent core in feminine sanitary napkins. By virtue of the large surface area and porosity, it is found that electrospun nanofibers provide a better alternative to achieve even higher absorbency, that too without adding superabsorbents. Sanitary napkins without superabsorbents can be a solution for its safe disposal. Second, in healthcare, amphotericin B-loaded nanofibrous oral tablets for the potential cure of leishmaniasis. Amphotericin B is an amphipathic macrosized drug molecule, highly preferred as a primary cure of visceral leishmaniasis and mycotic infection. The oral administration of drug is abstained due to its hydrophobic and self-aggregative nature. Due to this, it imparts nephrotoxicity and has very less bioavailability inside the GI tract. So, we aim to deliver this drug orally in such a manner so as to improve its bioavailability and reduce the toxicity. At first, we accomplished the fabrication of amphotericin B-loaded gelatin nanofibers via electro spinning. The nanofibers were then cross-linked with glutaraldehyde vapors for a few minutes to improve its water stability. As nanofibrous mat could have given fast release due to its high specific surface area, we introduced for the first time the compression of nanofibers into a tablet by using hydraulic press and further coating the tablets with sodium alginate in order to impose drug diffusion barriers. When the release study was carried out in realistic pH condition, mimicking the physiological conditions of stomach, intestines, and duodenum, we found a zero order profile with 100% drug release achieved by 96 hours. Further, these oral tablets of amphotericin B were found to be non-toxic to kidney cells due to slow and sustained release of amphotericin B. In case of oral tablets, the release rate was found to be dependent of degree of cross-linking of nanofibers, the compression pressure, and the thickness of alginate coating. Next is diclofenac sodium-loaded cellulose acetate-based nanofibrous transdermal patches for relieving muscular pain. Diclofenac is an anti-inflammatory non-steroidal drug which undergoes into first pass hepatic metabolism after its oral administration. Therefore, it is frequently administered to maintain the therapeutic concentration. However, the frequent dosing of diclofenac may result in peptic ulcers and intestinal bleeding. So, we aim to deliver diclofenac transdermally to treat local muscular pain. We loaded diclofenac into cellulose acetate nanofibers, which are hydrophilic in nature and would give a fast initial release. Tuning the surface wettability would give slower release. Thus, a novel and facile concept of micro-patterning of nanofibers using nylon meshes was introduced. The drug-loaded nanofibers were deposited over micro-patterned nylon meshes of different thread spacing as 50 and 100 micrometer. It was observed that the fibers deposited over 50 micrometer spaced nylon mesh showed lower wettability compared to other depositions, including non-pattern mats and thin films. Interestingly, the air trapped inside the interstitial spaces of nanofibers played a major role to control the burst release of diclofenac, which was not desired as it would have caused local toxicity due to its high concentration. Thus, we introduced a cost-effective technique to obtain pattern nanofibers, which can easily change the wettability of nanofibers and ultimately the drug release kinetic. On similar trends, we fabricated natural drugs, honey, and curcumin-loaded multi-layered nanofibrous mat as a wound healing biomaterial. Based on the mutual solubility of drugs and polymer, the sandwiched mat were fabricated, comprising of top and bottom layers of curcumin-loaded cellulose acetate nanofibers and middle layer of polyvinyl alcohol loaded with either honey or curcumin and both the drugs together. The tracing characteristics infers that the selection of polymers in the multi-layered assembly assisted in quick absorption of wound exudate and high water absorbency. Compared to the pure components, the synergistic activity of honey and curcumin further enhanced the antioxidant activity up to 93% and exhibited moderate potential to eradicate E. coli infection. Thus, layered assembly can be used to deliver multiple mutually insoluble drugs to enhance the therapeutic index. Moving to the tissue engineering field, let us discuss about hydrophobic electrospun membranes for eyelid cell encapsulation. As we know, diabetes mellitus is an autoimmune disease in which the pancreatic cells either stop producing insulin because they are destroyed by the immune system, or produce insulin that is insufficient for the body. Here, we demonstrate a fabrication of polymer membrane that has pore size 0.3 to 0.6 micrometer, vital for an active exchange of essential nutrients such as insulin and glucose while ceasing the infiltration of body's immune cells. Also, we introduced hydrophobicity to inherently hydrophilic polymers, which aided in maintaining circular morphology of eyelid cells to maintain a 3D architecture. Next, in agriculture, we fabricated neem oil encapsulated polyurethane nanofibrous bags for seed storage application. The blend of neem oil and polyurethane in dimethyl formamide solution was prepared and electrospun to obtain the nanofibers. Due to structural integration of neem oil into the soft segments of polyurethane, the load carrying capacity and elasticity of nanofibers was enhanced, which was in comparable range with commercial seed storage bags of polypropylene. When the real-time applicability of these bags were investigated, we found that after 75 days of seed storage, nearly 70% seeds in commercial bags were infected with black mold or storage-borne fungi, whereas only 10% seeds in nanofibrous bags were infected. The reason was found to be the controlled moisture transmission rate achieved through nanofibrous morphology and pesticidal property imparted by neem oil. This nanofabric bag show a great potential towards reducing the seed storage losses and may be a game changer for achieving food security as one of the goals for sustainable development. Coming to the sensors, PAN PMMA block copolymer derived nanoporous carbon nanofibers for hydrogen detection. In this, first we prepared nanofibers of PAN and PAN PMMA block copolymer. The adsorbent nanofibers then heated at 180 degrees to anneal the PMMA phase. In order to retain fibrous morphology, the nanofibers then exposed to ultraviolet radiation to degrade PMMA. The PMMA phase was then aged out in acetic acid solvent to obtain nanopores. Lastly, pyrolysis was carried out to get nanoporous carbon nanofibers of PAN. Now, for the fabrication of sensor, zinc oxide nanostructures were grown on P-type silicon substrate, onto which the interdigited electrode pattern of gold was deposited using thermal evaporation. Then, carbon nanofibers homogeneously mixed in isopropyl alcohol was drop casted on zinc oxide nanostructure. It was found that the nanostructure-based sensor enhanced the sensing response of hydrogen gas at 100 ppm to 74%, which was only 3% in case of carbon nanofibers and 44% in case of zinc oxide nanostructure. This is due to the formation of PN heterojunction at the interface of carbon nanofiber and zinc oxide nanostructure. Further, presence of oxygen functional group on carbon nanofiber surface contributed in enhancement of sensing performance. Now the last one is porous nanofibers based electrochemical immunosensor. Here we first prepared nanofibers of polystyrene polymethyl methacrylate block copolymer. As described earlier, the PMMA phase was thermally annealed, then degraded by UV exposure and aged out in acetic acid to achieve mesoporous nanofibers of polystyrene. The porous nanofibers displayed the presence of higher surface concentration of carboxyl groups needed to bind with biotin. For this, we first activated the specific binding site by using EDC NHS chemistry. The biofunctionalization of biotin was carried out by treating the surface of nanofibers with biotic hydrazide solution. And then non-specific sites were covered with BSA. When the immunosensing was carried out, it was found that the mesoporous nanofibers increased the sensitivity of streptavidin to 6-fold. Thus, we employed 3-step process to separate a polymer phase from block copolymer and obtain controlled nanoporous and mesoporous morphology, which can be utilized in wide array of sensing. This is all about the brief summary of our research work. I would like to acknowledge all our funding agencies and collaborators. Thank you everyone for your support and for the kind attention. Over to you, Akanksha.
Thank you, Dr. Mrinalini, for such an excellent presentation summarizing everyone's work on nanofibers from our lab. Our first eminent speaker is a pioneer in the field of nanofibers and does not need an introduction. However, for the sake of formality, it's my leisure to read his short bio. Professor Sriram Ramakrishna is the Director of Center for Nanotechnology and Sustainability and is among the top 3 impactful authors at the National University of Singapore. Listed among the top 3 scientists of the world in biomedical engineering as per the Stanford University Researchers Study on Career-Long Impact of Researchers. Thomson Reuters identified him among the world's most influential scientific minds. His Google Scholar citations are around 1,15,000 and Edge Index is around 160, something really extraordinary. Clarivate Analytics recognized him among the top 1% highly cited researchers in the world in material science and cross-field categories. Professor Ramakrishna received PhD from the University of Cambridge, UK. He is an elected fellow of UK Royal Academy of Engineering, Singapore Academy of Engineering, Indian National Academy of Engineering, and ASEAN Academy of Engineering and Technology. He is also an elected fellow of American Association of the Advancement of Science, ASM International, American Society for Mechanical Engineers, American Institute for Medical and Biological Engineering, Institution for Mechanical Engineers, IMechE, and Institution of Materials, Minerals and Mining, IOM3 UK, ISTE India, and International Union of Biomaterials Science and Engineering. He has co-authored several books and is on the editorial board of several international journals. He is regarded as the guru of electro spinning and nanofibers for diverse applications. He is also pioneering the intelligent biomaterials. Let us all welcome Professor Ramakrishna.
Thank you, Akansha, for your kind introduction, quite elaborate and detailed. And once again, thank you so much. Well, let me begin by congratulating Dr. Chandra, whom I have known for nearly 10 years. He has been doing wonders at IIT Hyderabad, and I get routine alerts about his progress every few months. So I like to say that I wish him stronger, much more success in the years ahead, and hope to see that Dr. Chandra, all his team members, build on this progress, which is very solid for the last 10 years, was presented briefly in the beginning of this seminar. I'm very sure that in the next 10, 20, 30 years, you can make a much more impactful, game-changing contributions. On your 10th anniversary, I'd like to join others and congratulating you. You're doing well, and we wish you to do even more well. Perhaps no sleep, work even harder. Okay, so the topic I chose today is future healthcare technologies, intelligent materials and systems. As was just briefly introduced by Dr. Chandra's team member, electrospun nanofibers have a wide variety of applications. We have been investigating them for the past 25 years. Every year I come across much more innovative, better ideas from other researchers. So to cover every aspect of electrospun nanofibers would be challenging in 30 minutes given to me. So I intentionally chose a far-sighted concept, what we can do using electrospun materials. Let us begin. I think today I'm here in Singapore, you're all in Hyderabad, and there are participants from all over the world tuning into this webinar. It is possible because we have a technology which are helping people to connect despite the social distancing and horrific effects on human health. You could see here Today, close to 2 million deaths and more than 100 million people got affected due to COVID-19. So this clearly brings the point, human health and wellness are impacted by infectious diseases. The history of humanity clearly suggests we have several episodes of such infectious diseases. Moving forward, there would be many more. So infectious diseases will continue to be an important topic for the scientific community as well as the humanity. There is research going on in terms of electrospun materials for viral, antiviral face masks in our own laboratory. But I would not be covering that in this presentation because I'm focusing on intelligent materials. And infectious diseases, even though they are big in terms of the impact, there are other things that are equally impacting human life. There are general injury and disabilities, lifestyle diseases like diabetes, genetic disorders, aging, and mental stress, which is becoming an important topic. So with that backdrop, I'm going to say that these are the variety of disorders. There's a book on left side we just authored. It got published just this month. It captures lots of details, but the essential point here is diseases, disorders, disabilities are associated with every tissue and organ of the human body. And then aging, here is a simple illustration of aging on bone density, and that varies between a male and female, and also how it changes with age. You notice the sweet spot of 20 to 40 years, bone density seems to be the highest. So here I chose myself as a test personality and look at using a simulated software how I might look in the future. No doubt, I look like that on the left side. You all agree, of course. And on the right side is a simulated one, how my skin will look like. But beneath the skin, which is a surface, you would see we have a variety of tissues and organs. And how do they age? What are the changes and noticeable things we can observe? Of course, you can understand this from observing, talking to the family members, other senior people in your own family. The important point here is between males and females, there tend to be different kinds of aging. So the medicines that have been developed with the men in mind need to be redeveloped so that the other half of the population also can get the benefit. So in addition to the gender, genetics plays an important role, lifestyle, and a climate. So I will not go through all these details, but that's meant for the future talks. If Akansha still decides to invite me in the future, I will give those talks. So with all the diseases and disabilities, last 50 years, between 1950 to 2000, a variety of medical devices have been designed and used. And then last 20 years, where we're also deeply involved, topics like tissue engineering, regenerative medicine, nanomedicine, stem cells, diagnostics, and bioprinting. The main purpose of these technologies and R&D is to regenerate diseased or affected tissues and organs. And of course, you already see some of the luxury skin care brands. This is a friend of mine, a German, Augustin Bader. He just launched a skin cell-based skin products. I'm not marketing his product, but I wanted to show you that research like that sometimes will have other wellness implications. Now, central topic of my presentation is, so what is the future? So the future of biomaterials, I tend to believe, would be intelligent biomaterials. That would be the focus for the future next 30 years. And I take the confidence in saying this from observing the nature. You are all familiar with Touch Me Not plant, and that's a basic, simple illustration of certain level of intelligence in the plants. There are books now emerging, as well as scientific evidences are coming, which talks about other living beings having a certain level of intelligence. So for the sake of our seminar and for the benefit of all the researchers, we recently published a paper which defines what are intelligent materials. So within intelligent materials, we define intelligent biomaterials are capable of processing external and internal signals in order to take actions that maximize the chance of successfully achieving the goals. It's a very broad working definition. If you use that and now start looking at biomaterials, you would be totally surprised what is possible in the years ahead. So to make this point, why do we even need this intelligent biomaterials? I want to show you this slide, something about intelligence, how it changes with age. So I paused a moment because I really wanted you to pay attention that intelligence apparently is a function of age. And many of you are in the right age profile. I would imagine you are in 20s to 30s. That is a peak of your intelligence performance. I'm sure that this is an opportune time for you to contribute and surprise the world community by your innovative research. Also, I like to make that in a much more simplified way. If we had to call that intellectual efficiency, this is a middle band where intellectual efficiency seems to be at the peak. And after that, once a person passes the middle age, there is a certain level of compromise in the intellectual efficiency. So in addition to that, there is another issue is the mental stress. COVID-19 clearly made the point that air, water, and food are essential. In addition to that, humans need social interactions. Otherwise, isolation, social distancing is causing them mental stress. And on the right side, you actually have a small illustration. If you are unstressed, you have a better control of your thoughts and emotions. When you are stressed, you have a less control on your thoughts and emotions. To look at these thoughts, which are source of your stress, roughly there are 6,000 thoughts per day that goes through your head. And in other words, it's about 4 thoughts per minute. They are number of thoughts in a minute. So as I speak and as you listen to me, in your mind, several thoughts are crossing. So interesting thing, 70% or to 80% of them have a negative content. More than 90% are actually repetitive, like the thoughts you had yesterday or last week. So the good news is, if you know what is thoughts and how you can manage them, you would be able to somewhat alleviate your mental stress. So here is the much more deeper scientific approach, where in the center I have thoughts and emotions, and they are shaped by a number of variables. And we don't have time to go through each and every one variable, but I like to say that thinking and intention, you could use as your tool to control your thoughts and emotions. In a way, you are able to change your mind. So in the future, next 30 years, humans will have access to refined devices, systems, and methods to perceive own thoughts and redesign own mind. It's a big statement, but this is a futuristic talk. So it is meant for inspiring future researchers like all of you to think about what can you do and make a difference to the humanity. So here are the glimpses. AI, artificial intelligence, neural interfaces. I will be giving you some more details, quantum chips, quantum biology, psychedelics, wearables. I'm going to give you some more examples on that, on augmented brain. So lots of research is happening. And with these advances, there is a potential to redesign own mind in the future. So right next to me, you have a Sofia Robot. which can emulate close to 20% of our current human abilities. So by 2050, I think there would be much more seamless integration of living tissues and organs with the engineered systems and digital technologies. So let me give you two examples. One is invasive applications, other one is a non-invasive applications. Invasive means involving, or that means they're, they're inside the body. So at the basics, this is how the neurons and then biochemicals that underpin our thoughts, our feelings, and our actions. So here is an illustration how neurons from external surfaces, for example, fingertips, how they're connected to the brain through the spinal cord and the mechanism of action because of these neuronal actions and the biochemistry associated with them. We are able to sense, we are able to react, we are able to perform certain actions. So that's a typical human brain of a person holding in hands. You can see it. And the point here is now we are able to design these neural interfaces. One of my PhD students, she is Chen Wang, she just completed her thesis in this topic. Here you see a number of neural electrodes that are designed to interface with hundreds of billions of neurons and trillions of junctions, what we call synapses they form in our body. So these neural interfaces are meant to interface with these neuronal bundles and tap the signals so that we understand how the neurons are communicating, what precisely they are communicating. So, and there are issues, for example, interface between biomaterial and the neurons. And then we use advanced nanomaterials like carbon nanotubes, graphene, PDOTs, many other material systems. And we nano-engineer the surface so that the neural interface is much more good. Here is an example how impedance is reduced by 50 folds at 1 kilohertz using a combination of PDOT and CNT nanotube, which is actually electrospun. So these are meant to guide the neurons to get into these electrospun tubes, and then interfaces are modulated so that we have a better signal to noise ratio. So these are the results, but I won't go through the results because of the time. So these are just to give you the convincing how this experiment is done. And this is done in the animal studies. And we actually recorded the signals, and we have shown how we can see the response of the animal for different conditions. And then that shows hot and cold and different stressful conditions. And then we can reverse this to deal with the neurodegeneration that happens with the aging process, and we call the neurogenesis process, enhanced by autophagy signaling by the neurons. So these are all published work. You can check at the cited papers. So the main message here is such neural interfaces will further enhance a number of medical devices that are already in use for health and well-being of human beings. So in the future, as I said, there will be much more seamless integration. And for you to believe, I want to give a real life example. This is Elon Musk, who is more than $100 billion wealth person. He is behind Tesla car as well as a SpaceX program. He also has a company called Neuralink, which designs the neural interfaces to tap the signals, modulate the signals with the purpose of treating people with Alzheimer's, dementia, as well as depression. So when you have such a deep-pocketed people supporting this direction, as well as investing resources, I'm very sure with the talented scientists that are listening to this seminar, there would be much more progress so that we will have a much more advanced systems that helps us to understand our own mind and brain in the future. Now I'm going to switch to non-invasive approach. So far I have shown you an invasive approach, here a non-invasive. That means we're not actually going inside the tissues and organs of the human body, but we're actually on the outside. So a number of wearable devices are already in the market. Fitbit is one good example, which people are already using. So here, electrospun nanofibers have been made into wearable devices. In this case, for example, a ring that wraps around the fingers. That can be used for measuring or monitoring heart rate, body temperature, respiration rate, glucose levels in the breath, as well as the body motion. So these are all possible. And so when you have such an advancement, we can move away from centralized healthcare monitoring to a personalized remote healthcare monitoring. And you already see the evidence of this in COVID-19 situation, where the patients are isolated, but their vital signs are monitored 7/24 hours for the action by the medical doctors as well as the local communities to keep everybody safe at the same time to treat the patient. So here is a classical example of wearables, initial glimpse, what progress is possible and why they are needed. And here I'm convincing you to show by showing a variety of electrospun materials, different material systems, in this case PVDF, PDMS, as well as many other materials that have been electrospun successfully. These are different mechanisms we can use to leverage high surface area, small dimension nanofibers of a particular materials and harness particular sensing ability using their basic concepts like piezoelectricity, capacitance change, piezoresistivity, as well as contact resistance. There are many other aspects we can leverage by having these materials converted into electrospun nanofibers and building devices from them. So here is the results. You can see these devices successfully used for measuring the heart rate, also glucose level from the breath, and respiration rates, temperature monitoring, and body motion. Later on, you can use the similar concepts, electrospun nanofibers, integrate that into textiles, and then you can generate necessary energy to run these devices. So I'm giving an illustration that you can make a self-powering devices so that you do not need an additional battery. And imagine in the future, if you have these devices powering implants, for example, pacemakers, which tend to be deployed inside the body for anywhere 5 to 10 years. After that, a person need to go for a revision surgery so that pacemakers of the heart and brain can be replaced for the new batteries. So in the future, if we have wearables which can self-generate and do not need a complex battery systems, we have a better and improved quality of life. So here is a few more examples of flexible electrospun silk-based wearable system, and more examples of electronic skin that is made out of this one. And this is similar how that has been used in analyzing for the case of diabetes from the breath. And here is for the medical bandage. Just now, the first presenter talked about wound dressings. One of the problems with the wound dressing is the bacterial infection. Second one is the doctors would not know unless they peel off the dressing to know what is the relative healing rate of the diabetic wound. If you have a future smart wound dressing that can give out the information about the microbial community. At the same time, it also can give out the information about the wound healing. It is enormously helpful to the doctors as well as the patients. So recently, we just published a paper. It came out today, where we have electrospun systems using a perovskite material that can be used for harnessing sunlight and produce energy that is needed to run these devices. Again, I like to give you one good example about this wearable technology. Just now, Google announced they're going to buy Fitbit with a $2 billion. So what that means is, again, wearables also seeing a massive injection of funds by the entrepreneurs. There are lots of researchers in the world pushing in the direction of wearables. Many of these wearables right now, they're not really flexible, they're not breathable, but moving forward with electrospun materials as well as other fibrous structures and geometries, future wearables would be much more comfortable and much more desirable by the human beings. So in conclusion, all I like to say is I predict intelligent biomaterials will further enhance the healthcare outcomes of the human beings and well-being. So if you are looking to contribute in this direction, there's a lot of areas still require intense research. I hope you'll have a fruitful time doing that research. So to give a graphical illustration, so far we've been focusing on health, and wellness is becoming extremely important, and intelligent materials and systems will play a very significant role in the coming 10, 20, 30 years. Well, this is what the mural at a university, I gave a lecture, a French university yesterday. There is a mural which talks about the future of life 2050. And you can see there is a Taj Mahal behind me, and then Eiffel Tower there, and then lots of other stuff there. And this right in front of me is Singapore. And so that's Malaysia and whatnot. So I think they think the world will be covered by snow, but I'm not so sure about that. But I'm sure we'll have much more interesting intelligent systems, and then you'll have a wonderful future life. With that, I like to say thank you so much for the opportunity, and I hope there is some level of interest in what I said, and I hope all of you can change the future by continuing your passion the way you are doing. Again, I like to congratulate Dr. Chandra for his passion, never-ending, no-sleeping drive to run the Carbon Lab at IIT Hyderabad. I hope you will continue to do that for the next 20, 30 years. All the best.
Thank you. Thank you so much, Professor Ramakrishna, for such an interesting and insightful talk. We hope all the viewers will contribute actively in this research area, as most of us are at the peak of our intelligence. So again, I would like to request all the viewers to post their questions in the YouTube chat box. We will take them at the end of the webinar. So moving to the next speaker of today's webinar, we now look forward to Dr. Nissa Saleem's talk. Dr. Nissa Saleem received her PhD in Material Engineering from Deccan University and is currently a Vice Chancellor's Initiative Research Fellow at Swinburne University of Technology. She has published over 35 high-impact journal papers, 3 book chapters, and 1 patent. She has been recipient of several awards, including the latest Phillips Law Postdoctoral Award of Award 2020 for the Physical Science by the Royal Society of Victoria. She has awarded with the Excellence in Scientific Research by Early Career Researcher in the Physical Science within 7 years of completing a PhD from the Victorian Research Institute. She develops multiple functional materials with nature-inspired design to solve challenging problems. Dr. Nissa Saleem developed the material in various lengths and dimensions, creating working prototype or devices using a novel molecular self-assembly approach. So without wasting the time, let's welcome Dr. Nissa Saleem to enlighten us with her presentation. Welcome, Dr. Nissa Saleem.
Thank you, Poonam, for the very kind introduction. I hope you can see my presentation. Can you?
Not yet, ma'am.
No, not yet. Yeah, it's coming now.
Okay. So thank you. So before I start, I'd like to thank Professor Sriram Ramakrishna for the excellent presentation. I find the talk is very inspiring and motivating, especially he mentioned about how best we should best use our thoughts and emotions, and in the future how we can how we can access to the devices. So these two things I find very striking. And I'm pretty sure that maybe in these days I will be brainstorming a lot about the intelligent materials and how well I can utilize my emotions and thoughts. So thank you so much for the fantastic presentation. And again, the next is I'd like to thank Dr. Sharma for the invitation, and congratulations Carbon Lab for the successful 10 years at IIT Hyderabad. And I feel very privileged to be part of Carbon Lab. Because it's been almost 2 years we started the collaboration, and we currently have 2 joint PhD students. So I'm sure that in the future we would be strengthening our collaborations through Dr. Sharma's Carbon Lab in a number of ways. And I wish all the best to the group's all future activities. Okay, so before I start, I would like to talk a little bit about Swinburne University of Technology, its location and structure. So our university is located in Melbourne. That's a part of a state called Victoria. So it's the same state where University of Melbourne, Monash, RMIT, and Deakin University are located. So Victoria has been regarded as the education stage. So we have 3 campuses in Melbourne and 1 in Sarawak, Malaysia. We have 3 faculties in the universities where 19 departments are part of it. We also have 15 research centers, 5 strategic research institutes. So Melbourne is the most livable city with quality healthcare, education, culture, and infrastructure. So this is a perfect place to consider for study and live if you are interested. Okay, so now coming to my presentation. So I've been working on carbon fibers for more than 5 years. So I'll be discussing some of my research activities we have done in this space. I will be also covering some of the current research activities that I'm doing at Swinburne University. So I thought it might be interesting for Carbon Lab's activities. So carbon fibers and carbon fiber reinforced composites are important class of materials in the areas where weight reduction and fuel consumption are necessary. So automobiles and aerospace are the major industries seriously considering weight reduction of cars and aeroplanes. This is mainly to reduce energy consumption and carbon dioxide emission. So carbon fiber composites provide considerable weight reduction and excellent load carrying capacity while maintaining the strength needed to withstand internal pressures. So those who don't know, carbon fibers are synthetic fibers, look like human hair. So as I mentioned before, these are important materials in the area where weight reduction and strength are necessary. So as you can see, there is a comparison between carbon fiber with human hair. So the diameter of the carbon fibers are around 5 to 7 microns, so which is around 10 times smaller than human hair. But when you consider the strength, it is about 8 times stronger than steel. So here is a quick representation of carbon fiber production. The starting material for the production of carbon fiber is a synthetic polymer called polyacrylonitrile or PAN. So currently, about 90% of carbon fiber production is from PAN, mainly due to the good carbon yield and its stability. So this PAN undergoes a process called wet spinning. So here we are extruding the polymer in a solvent that's called a coagulation process, and that's the way it forms a white fiber or precursor fibers. So these precursor fibers, when experience high temperature treatment over 1000 degrees, then form carbon fibers. So these carbon fibers later embed in a polymer matrix and make structural composites. So there is a strong demand for carbon fiber manufacturing industries to meet the demands arising from various sectors. But the challenge is, though carbon fibers are known for more than 40 years, most of the details about carbon fiber production is still unknown, because the exact composition of each PAN fiber varies from one company to another and is generally considered as a trade secret. So we only have some indications like the quality of the carbon fiber is directly dependent on the precursor. About 90% of carbon fiber production is from polyacrylonitrile or PAN, and this PAN will have 2 to 10 weight percentage of co-monomers contents in it. The choice of the PAN co-monomer polymer, it has to have a certain molecular weight that has to be between 100,000 to 200,000 with a polydispersity index of 2 to 3. And again, the composition, so the sequence of the co-monomers and this PAN chain, that also matters. So to better understand more about the precursor science and also to convert these polymers into the fibers, we work with our international collaborators. So with the support of government funding, we carried out this research. So we have designed and synthesized a number of highly controlled PAN in collaboration with University of Southern Mississippi for high performance carbon fiber production. So once we design and synthesize a polymer, the next stage is the spinning process to convert the polymers into a white fiber. So this wet spinning process involves many steps, and we have to consider a number of process parameters. So again, the exact spinning formulation of these fibers are usually confidential. Then we have conducted all the carbonization studies back in Australia. So we made a comparative study by selecting 3 co-monomers, and we carry out the synthesis by using both conventional and controlled polymerization techniques. So we have included both acidic and neutral co-monomers in our study, such as itaconic acid, methacrylate, and methyl methacrylate. And we have used free radical as well as raft polymerization methods for the design and synthesis of all these polymers. So once we completed the synthesis, we have conducted stabilization studies on these polymers. So this is a process which is the most critical and time-consuming step in the carbon fiber manufacturing. So during this stage, the fibers attain its stability to withstand high temperature carbonization. So we found that the polymers synthesized by controlled polymerization promotes cyclization reactions, thereby stabilization process. So once we synthesize the polymer, converting these polymers into white fiber is the critical part in carbon fiber production. So to learn more about wet spinning process and to get the training on the pilot scale fiber spinning facility, I was visited University of Kentucky. So this, the spinning facility at University of Kentucky is a very specialized one, and they have more than a decade of experience in fiber spinning and fiber science. So we have conducted various spinning studies by changing the coagulation conditions. So in our study, so we used 80% of organic solvent. In another study, we changed the bath concentration to 77.5. And we also developed a new method to measure the porosity of the fibers during the fiber spinning process. So please, if you are interested, please check our article to learn more about this porosity measuring technique. So here is the picture of carbon fiber production line at Deakin University. We have carried out the stabilization and carbonization process in this production line. So here is the work where we carbonized the fibers we spun at University of Kentucky. So you can see that by making a slight change in the spinning condition, that is the coagulation conditions, that can affect the final carbon fiber properties. We were also interested to make changes in the carbon fiber production line, or try using alternate precursor fibers to come up with cost-effective ways to make carbon fibers. So in one study, we applied a higher tension by using a lower temperature in the furnaces, and we wanted to check the final carbon fiber properties. So we found out that we come up with an automobile grade carbon fibers just in the lower temperature furnace. In another study, instead of using the normal carbon fiber precursors, we selected a textile grade PAN fibers, which is much cheaper than carbon fiber grade 1. And in the study, we come up with a tensile strength of 3.25 gigapascal and a modulus of 245. So this work is currently considered to publish in Polymer Degradation and Stability. So it has been reported that carbon fiber anisotropy can cause premature delamination between fiber and the matrix, especially in some high stiffness composites. So this happens mainly due to the fiber's unique microstructure and the graphitic carbon. Between the graphitic sheets, there are packets of amorphous carbon and voids. So although the tensile properties of carbon fibers are readily measured through robust and direct techniques, but the determination of transverse properties of the carbon fibers is very complex because the diameter of the fibers are so small. So to address these issues, we come up with an approach. It's a very simple and direct method to measure the transverse and longitudinal properties of carbon fibers through micropillar compression. So here is the typical example of the micropillars by focused ion beam milling, both in longitudinal and radial directions. So here is the fractured micropillars after the compression. So we have conducted these studies on 3 different carbon fibers with various modulus. We found that tensile stiffness was significantly higher than the compressive stiffness in all these 3 fibers. And there is a connection between the degree of crystallinity with the stiffness properties. So further in my research, our target was to make high performance fibers. So an ideal fiber is one that will have very high strength, modulus, damage tolerance, and compressive properties. So as you can see from the figure that the fiber will be free from all defects and impurities. So though carbon fibers are high strength materials, the mechanical strength of the current carbon fibers are limited by presence of voids, defects, and impurities in their fiber structure. So theoretically, it is estimated that carbon fibers can be made 10 times stronger than currently available fibers. So one approach is to reinforce PAN with carbon materials like carbon nanotubes, graphene oxide, etc. So we used graphene oxide as the reinforcement for enhancing the properties of the fibers. So here is the picture of the fibers produced by mixing PAN with various amounts of graphene oxide. Also the representation of wet spinning instrument we used for producing these fibers. So the SEM images of the fibers confirmed that the fibers are free from any cracks or any damages, and we could make kilometers long continuous fibers with significant improvement in mechanical properties. So in the study, we have come up with around 115% improvement in tensile strength and also 150% improvement in tensile modulus. So we are still continuing the carbon fiber research in collaboration with Deakin University. Okay, so now I'm going to talk more about my research focus at Swinburne University. So here my research is more about functional carbon materials, where the structure of the materials are very critical. So we make carbon materials in different dimensions, such as fibers, films, and foams. So we want these materials to be multifunctional. And the approach we are using in this research is a self-assembly approach. So here is the summary of our approach to make these multifunctional carbon materials. So we start at the molecular level, where we design and synthesize polymer molecules and direct them to self-assemble. So we introduce special chemical functional groups into these molecules and make them interact. So that means we introduce attractive and repulsive forces among these molecular chains. These molecular interactions lead to make nanoscale structures that you can visualize using high-resolution microscopes. So these nanostructures can be created in different shapes and sizes and are highly stable and organized. We then introduce these nanostructures into microscale materials while preserving the order at nanoscale. So we can create fibers, films, or forms using the same approach. Finally, we develop macro-scale structures or devices to demonstrate the application of these materials. So we create working prototype of these devices or structures. So all these research is followed by the fundamental understanding of structure property relationship from molecular design through to functionality. To create structures or designs at nano levels, we use a class of polymers called blocker polymers. So these are the polymers that consist of two or more polymers bonded together by a covalent bond. So here is a representation of a blocker polymer, where the polymer has two units joined together called a diblocker blocker polymer. So these, because these polymers possess a covalent bond, the blocks in the blocker polymers cannot be separated or mixed together. But these blocker polymers can undergo a phase separation process, and that's the way they make structures at nano level. So here is a diblocker polymer called polyethylene block polyethylene oxide. So this is an amphiphilic blocker polymer where polyethylene blocks is hydrophobic in nature. So when such a polymer dissolves in water, so these molecules self-organize in such a way that all the hydrophobic parts form the core and the hydrophilic part forms the shell. So that's the way they form spheres-like particles at very nano level, and they are called micelles. So I'm going to show you some of the examples of nano structures we created in our research using blocker polymer self-assembly. So these are spherical structures formed from a diblocker polymer. Here the polystyrene chains form the core and PU forms the shell. In this study, we come up with very unique thread-like micelles formed by blocker polymer self-assembly. We also prepared compound vesicles for the first time by using a mix of polymers and polyelectrolyte complexes. So as you can see, the structure consists of many tiny vesicles encapsulate inside a giant vesicle. We also prepared interconnected vesicles where you can see the channels connected using polymer chains. Another morphology we developed is a vesicle that is called entrapped vesicle. That is, you can see one vesicle is entrapped in another vesicle. So we used various combination of blocker polymers for the design of these nanostructures. These blocker polymers can also form these nanostructures in their solid state too. So these are the major nanostructures they form in their solid stage. So in addition to this, they can also form hierarchical structures such as sphere in lamellae, lamellae in lamellae, etc. So here is a couple of examples where we fabricated highly ordered nanostructures from direct self-assembly of blocker polymers. We have fabricated honeycomb-like features. We also fabricated lamellar-like nanostructures. So these structures are heavily used in nanopatterning application and also for the fabrication of transistors. So you'll be seeing some examples of ordered nanostructures formed by direct self-assembly method. So in this study, we created rod-like features with hexagonal patterns from a triblocker polymer. This work shows formation of ordered lamellar structure. So the orange and blue color representation denotes the organization of different polymer chains. Here you can see some hexagonal arrays of nanostructures with size around 30 nanometer. So here we used a double crystalline blocker polymer blended with a homopolymer system. The last one is showing a hexagonal cylindrical arrays of polymer chains. So in summary, we have created various nanostructures both in solution and solid stage. So we can control the morphologies, or we can switch the morphologies by changing their molecular weight or chain length, or even their composition of each blocks in the blocker polymer. We have also derived a mechanism for these materials to understand the structure formation. So in the current study, so we adopting designs from nature to create various porous materials by using this self-assembly approach. So these nanostructures were translated into macro scale materials while preserving the order and self-assembly at nanoscale. So we developed functional fibers and forms using this approach. So the forms and fibers possess highly ordered, interconnected pores at nanoscale and microscale. We have also demonstrated application of these materials in sensing, energy storage, and absorption applications. So here we combine to use molecular assembly and also the ordered arrays of structures such as honeycomb-like features in a graphene form. So we made a nanocomposite form by combining polyurethane with graphene. So addition of graphene leads to the formation of ordered honeycomb-like features. So these forms exhibited excellent strain sensing properties. So we have demonstrated motion sensing capabilities of these materials like finger bending, walking, and jumping. So that shows its potential applications in pressure sensing areas. In another study, we have explored crystalline phases of polymers to make foams. So we selected polyvinylidene fluoride and we combined that with graphene. So PVDF has different crystalline structures. So we found that by altering the polymorphism of PVDF, we can exert different modifications on their physical properties like thermal stability and electromechanical properties. So in the study, we demonstrated how the crystalline transformation of PVDF influence aerogel formation. And this material exhibited compression or compressive sensing properties. We were also interested to look at structural features to make porous carbon materials. So in this particular study, we followed a soft templating process by using blocker polymers. So here the target was to make tunable carbon nanospheres with uniform porous structures. So you can see that the pure blocker polymer exhibit rod-like features, but as the reaction proceeds, the morphology was changing from the thread-like features to spherical-like features. And we use these carbon materials as the electrodes for demonstrating energy storage applications. So in our current research, we are combining self-assembly approach with adding functionalities. So by using this method, what we are doing is we are converting the two-dimensional carbon materials into three-dimensional forms. So in this particular work, we have used a electrospun mat into a three-dimensional forms, and that's the way we found that a highly interconnected network of nanofiber features that's the way we can bring efficient high oil adsorption or chemical adsorption capabilities. We also wanted to look at what will happen when we scale up self-assembled nanostructures at macro scales. So we have demonstrated this to make functional fibers. So here we designed marine sponges like functional fibers. So these fibers exhibited meso, micro, macro-sized porous features, both the surface and the cross-section of the fibers. And these fibers exhibited high surface area. And we also checked the adsorption and energy storage properties of these fibers. Okay, so before I finish, I'd like to highlight another exciting research that we do in collaboration with CSIRO. So we are working on developing multifunctional value-added materials from animal byproducts and waste streams. So the focus is on exploiting protein materials, especially collagens. So you might know that collagen is the principal protein in animal body. So it's one of the major components of bones, tendons, and ligaments. So here is one of the outcomes of our research in this area. So together with CSIRO, we have successfully established sustainable and environmentally friendly methods to extract collagen from chicken byproducts. And we use that extraction to make carbon fibers, and we come up with highly porous carbon fibers. So these are the ACM images. So you can see that the fibers we created were very, very flexible. So in our approach, so we use very environment-friendly materials and process to create opportunities in circular economy. So we are continuing this research, and we also come up with not just porous carbon fibers, but we also find that the approach is very beneficial to make sensors and similar kind of value-added materials from these waste products. So in summary, so currently I'm working on a wide variety of material designs, including self-assembled structures functional porous materials, and we are trying to make these materials multifunctional. So we were able to create very interesting morphologies and trying to maintain the order at macro scales. So most of the studies are currently under investigation, mainly to understand the material structure and their properties. So that concludes my presentation. So finally, I'd like to thank past and present collaborators, my mentors, my funding bodies, and more importantly, my team members. Thank you.
Thank you, Dr. Nissa, for such an inspiring talk. I'm sure all our viewers are much more educated about carbon fibers and various nanostructured carbon materials now as they were before your presentation. At least I know I am much more educated now. So now we'll take the viewers' questions one by one, and we'll try our best to pick up the maximum questions allowed in the available time frame. So the first question is for Professor Ramakrishna. It's by Mr. Alok Srivastava. He asked, can you provide some more information on the mechanism of self-powered variables which are being explored and which will be useful for onboard power generation?
Thank you, Alok. I hope you can hear me. The concept of self-power generation has several mechanisms. If we use, let's say, a motion, you can arrange two surfaces which would respond piezoelectricity, and then you design the device to a level that produces the voltage to the level you need, as well as the amperage or the total power. The question is that the only mechanism? No, there are many different concepts are there. The whole idea is, don't imagine it is powering a large building. It is not. It is mostly powering small devices that would not require external power source. Second one, where the weight is an important issue. So to repeat again, the energy can be generated or harvested by different concepts. Could be relative motion, friction, change in the dimension, or change in the morphology, change in the electrical conductivity. So we use different concepts depending on the material we're going to select, depending on the application. Then you build a device and produce the energy generation. You can also extend this for managed thermal management. So if you design it such a way, you could also remove the heat away from the body. Should you design such a system, or you can also warm the body. So the wearables research is going in that direction.
Thank you, sir. I hope it answers the question by Mr. Alok. I have one question for Dr. Nissa regarding the collagen nanofibers. Could you just elaborate a little on the electro spinning of the collagen fibers, and what is the benefit of carbonized collagen nanofibers over the carbonized polymeric nanofibers?
Okay, so thank you for the question. First of all, I'd like to highlight that we haven't made collagen nanofibers, but we made collagen microfibers, because our idea was to make carbon fibers. So there's a difference between carbon nanofibers and carbon fibers. I think you might have seen my presentation. Yes. So the carbon fibers, when we say we are aiming at between 10 to 12 6 to 7 micron size. We haven't tried electrospinning mainly because collagen is a protein, and we know that by applying the electric, the power, we will be denaturing the protein. So that's why we come up with a wet spinning process, wet spinning approach. So what we did is we extracted collagen from chicken feet, and we use that solution for wet spinning process. So wet spinning, when I say, this is like we are converting that polymer solution into a solid fiber mat, and we are extruding that into a solvent. So that is the difference. We are not applying any electric power or anything, and that's the way we can preserve the protein, especially the helical features of the collagen. So the idea was that we wanted to use these wet spun collagen fibers for 2 different applications. So one is for the biological applications, and the other was we were curious to see what will happen or how much carbon we can preserve while we heat this protein material. And surprisingly, we find that we actually find some of carbon material. Probably Professor Sriram might know that the problem with the collagen is the thermal stability is very low. But in this wet spinning approach, we could actually maintain, but we have used some cross-linking to enhance the thermal stability of collagen. But we were very surprised to see, or we were very curious to look at the final porous carbon fibers features that actually coming from a very low price animal byproduct material.
Thank you, ma'am.
Can I just say something to support Nissa? Okay. So, I think her thinking is, I'm not sure whether she worked with Mino Nabe at Dakin.
Yeah.
She also works. She's my collaborator too. The point is, what you guys doing is excellent. The work, and one of the important issues is sustainability. And worldwide, right now, the materials generated carbon emissions is close to 20% of the total carbon emissions by the human activities. So the carbon emissions from the materials, a wide variety of materials, is an issue. And carbon fibers traditionally has a lot of energy intensity, and moving away from any traditional approach or conventional approach towards bio-based materials like collagen, what she said, it could be cellulose or something else. I think it's a fundamental shift in trying to reduce the carbon footprint. And I think with that, we all know that, Dr. Chandra would not choose a laboratory or a center named carbon unless he thinks that is the very important, right? He's a very smart guy. So I think I agree, because carbon has so many applications. It's enormous. And for example, I give an example. There is now biggest issue with the water pollution that requires you to remove endocrines, and the carbon plays a very important role. And that is a big deal for the continuity of the human population. Otherwise, the human population becoming sterile. So Singapore and Switzerland, they already fitted water treatment plants with carbon filters. I'm just giving an example. So now imagine Nissa makes the future carbon filter from biomass that is environmentally very friendly and nice. And I think that would solve at least an important issue, which is the unfriendly processes and material systems. Human beings got used to it for the last several hundred years. So moving forward, we need to go towards sustainable solutions, and I think that's where I believe what she's trying to do. It's a long answer. It's basically to support her.
Professor, Professor Sri, actually, I have a question to you.
Sure.
Because in your
Oh,
presentation,
by the
you
way, is the
mentioned...
panel members can ask each other the question? Is it allowed? Okay. Okay. You can ask.
Yeah, and I'm really, because while I'm presenting, I'm still thinking about, the intelligent biomaterials. See?
Okay.
I want to know, so in that context, so are you considering, or have you thought about to use bio-inspired or bringing nature-inspired designs or features into those materials? Or what is your, the thoughts on that area?
Yeah, you're right. Right now, the closest we could get there is we use the nature-inspired surfaces for antimicrobial modifications, but that's just the basic. And I think nature uses nano micro structural arrangements for it to be somewhat protective. The core message I actually understood about the life, I've just on the chat box, I'm messaging Dr. Chandra about life. The reason is when you understand life, all living beings trying to survive. So the survival mechanism is somehow is already built into the living beings, all living beings. That includes plants as well as all other organisms. So how are they doing that decision? Well, the humans think they are the most smartest on the planet, right? But you actually find very rudimentary organisms also able to defend themselves. They morph, and primarily based on the structural arrangement. So they actually adopt their own structures to deal with the harmful their own surroundings. So I could give lots of examples, but they're not my work. But I read a lot of brilliant work by others. But I need more people like all these guys around in this webinar to do the work because we only have 24 hours. We need more manpower, and there's plenty of ideas. But also we had to see where the funding based on the research funding. So main point what you're saying, which I agree, is that the microstructural arrangements at a different length scales would bring in a lot more self-generating intelligent behavior or response. And I think that we could use it. You could already see those in a 4D printing, where they talk about the structural rearrangement of a material, and then you make a 4D. Now they talk about 5D printing as well. So yes, I think there's a lot need to be understood. And there is one more thing, just to make everybody's life more interesting and complex. I use another term, quantum concepts. So we haven't even added the quantum phenomena to the materials. And if we start adding the quantum concepts, and then if we can scale it up from angstrom level, sub-nano level to the micro and macro levels, if we can harness that, that would be brilliant. So we're constantly thinking about, it's a very difficult subject to understand quantum biology. And but I think there is a lot of hope to pick up some of the ideas from quantum biology and other concepts and see whether we can build a system, material system, that can translate submicron, subnano functionalities or unique properties and behavior to the larger length scale. When we do that, I think we'll have even more material systems we never even imagined.
Yeah.
And of course, all these guys will get the Nobel Prize. That's the goal. Yeah.
Yeah, I think that's the kind of final destination for these all efforts towards biomimicking the actual systems.
Yeah, absolutely. And I think I believe that this fusion of multidisciplines is beginning to happen now. So if you look at the long history, I'm not here to tell the history of science, but if you look at it, let's say 500 years ago or before, You have few scientists, they almost dabble with all subjects. But the fast forward, last 300 years, each subject became so big. And even within subjects, so many narrow disciplines, everybody became specialists. But the problem with that is we're unable to leverage a lot more knowledge that's there in other disciplines. So the moving forward, I believe cross-disciplinary experts will emerge. So these are the guys, they like more than one subject. They somehow understand them, they put them together. And then they're able to design things much more interesting. So it's like this, somebody understands natural systems, and then he might be working on completely on a materials engineering or computer systems or interfaces. They might come up with something, performances, behaviors, and solutions we never even imagined. Yeah, I'm highly optimistic about those. Yeah.
But as per your slide, that's going to happen in the age of 30 to maximum 20 to 35.
Well, that's what I said, because after that I may not be around. So,
so that brings me one interest, because you have presented very nicely about this interesting fact about the intelligence with the age. So you said that the peak is something around 30s, and then of course, but then what about the experience? That doesn't bring the intelligence.
No, you brought a very important point. That there is two parts to it. One is a crystallized intelligence that tend to grow. That's probably you can call a wisdom or experience-based accumulation. There is something called fluid intelligence. That's more about the dynamic connectivity of the neurons. For the audience, I know you have a global audience. Some of them may not be familiar. Just give an example. Is this tiny brain has about 100 billion neurons, and they form about more than 1 trillion junctions. To give an idea, that's much more than the number of stars in the galaxy. So can you imagine our head has so many connections? And these are the one, it's dynamic. Previously, they thought you were born with a particular pathways of networks, but the more and more new research is these networks change with your experience, knowledge, and culture. Even much more interesting is language. The language you speak apparently change these networks. It's amazing. So what it means is there's a dynamic rearrangement that's happening. So now this fluid intelligence is a lot about that dynamic reconfiguration of neural networks. But I'm now beginning to see neural networks alone is not the, going to be, we should be after, because somebody was telling me, let's say there is inbuilt intelligence even if there is no neuron. So the cell, each cell is in our body, not the neural cells, the normal cells. They also know how to replicate themselves. So, but there is no neuron there. It could be other cells. So that means there is some level of memory intelligence. You could call it a rudimentary, it's there. So now we need to talk about intelligence more than nervous system. So probably we had to add the whole endocrine system, immune system together. So then the question is, your question is with age, is this the downhill for people after 35? Well, it is not so. In fact, that is a normal trend. You do nothing with the brain. But if you keep it active and keep attending webinars organized by Professor Dr. Chandra, I think that's it, right? And then you listen to all the speakers, the brain is already active. So I think it's a question of what do we do with it? If we can figure out a way of constantly nourishing it. And I showed one nice image where I put there lots of bubbles with lots of details. Actually, that's plenty of ways one could sustain the intelligence. Yeah. I use this slide is mainly because I always attend all these webinars I attended by young people like 20 to 30. I just want to tell them, guys, this is the best time. Don't waste time at all.
So
best time to work hard.
So there is a question also, why there is a decline in the intelligence with age? With the cumulative experience, human tends to improve their intelligence in some aspect like self-awareness, emotional knowledge.
Well, ask him if the person is in front of him. I'll ask him if he has seen any dementia patient, Alzheimer patient. It's very clear, right? They would not be the same level of him. So that means there is a decline of cognitive ability. So we should not confuse that with experience-based expert knowledge. For example, Singapore, if I've been living here for so many years now, right? Probably even if I have a bit of declined cognitive mindset, I still know where to go, how to go. I don't know which, I would definitely know which is the best coffee shop. Yeah. So if should you come here, I know which shop to take you. So that is more strong memory based, which goes into our what they call subconscious mind or subconscious brain. So that definitely helps in leveraging our ability. But there is something else is dynamic intelligence. That depends on the healthiness of the neuronal connections. What I was told with aging, these connections are getting modulated. So in a way, they are impairing your cognitive processes.
So maybe
So
something
it's a more in terms of understanding. There are complex mechanisms involved. In some sense, what you're saying is correct. The questioner, the way you asked is you are right. Obviously, the people with the age and experience seems to have a good knowledge or intelligence, but that's more about the wisdom and knowing the knowledge-based, experience-based knowledge. The other one is more about the fast way of thinking. I'm very sure if you ask the same question, Nissa, if she had actually studied all this, she would answer even faster than me, right, Nissa? Yes, she agreed.
So,
Right.
to take the discussion forward, Professor Ramakrishna, I have a couple of queries. Let's say, so what do you think? What is your opinion about replacing the artificial intelligence with respect to this human intelligence? What do you think? Can we really go for that extent?
Well, I spoke to the best experts at Carnegie Mellon Universities about 2 years ago, before I put that slide, because I want to be very sure, because the Sofia Robot is most quite a very popular robot worldwide. People have seen it in action. So I took that picture, and then I was also impressed with the Sofia Robot that was taken 2 years ago. And then after that, I had a chance to attend the AI conferences. So I asked the experts. So there is a variation. Most of them say current robots are nowhere close to the human intelligence, nowhere. But if you say the human have thoughts, emotions, decision process, if you amalgamate all of them, to integrate them together, I kind of feel they are able to match up to 10 to 20% of the human AI, human intelligence. But moving forward, are they able to match or surpass human level? I think in certain aspects, probably they would. For example, computing large numbers. If our brain can compute so many in a particular second, they probably can do that even faster. Then they have a self-learning, machine learning. These are algorithms built in, and they are able to self-learn quickly. So am I scaring all of the people saying, oh, eventually we will be overtaken by these machines? I don't think so. I actually think humans are much more smarter. And they even though all the Hollywood movies show that they're going to take over, that's something people want to see, or at least feel like a fantasy. My view is it's a long way off. Definitely not 2050, not even 2100. The humanity will be prevailing. Yes. So your point would be, if you say the AI and the human intelligence, how do I stack them? Human intelligence is a much more multidimensional.
Yeah. So last follow-up question on this. So when you see, of course, there is an aging effect we are talking about, and that's related to your intelligence. Is there any self-healing mechanism?
Sorry, the question?
Is there any self-healing mechanism?
Yeah, for the intelligence?
Yes.
Yes, there is something called neuroplasticity. So they say that even though, okay, maybe, can I show my slide?
Sure, yeah.
If I'm allowed to.
Yeah.
Sure. I'll just pull that slide and then do the slide share.
So all this yoga and all that helps in the self-healing.
Oh yeah, absolutely. I definitely think so. Okay, so let's see. They may be wondering, is it a nanofiber seminar or the yoga seminar now? Yes, right. Okay, guys, let's look at this one. So essentially, thoughts and emotions, and you look at sensory inputs, that is basically all your 5 senses. So constantly the eyes, skin, smell, ears, everything. They're constantly inputting inputs to your brain. And then there is genetics, like whom you're born to, and the biochemistry and age. Then your physical and mental health, like social isolation, definitely is affecting people. And then physical issues. Then there's the other one is lifestyle and diet. This is where India is doing very well. I think the traditional Indian diet is extremely nutritious and for the well-being of the physical body as well as the mind, absolutely no doubt. And in fact, there are a lot of people trying to understand the rich diet, which is plant-based diet India traditionally has. That seems to have an important role on the way the brain and mind works. And then there is something called subconscious mind. This is where you are storing lots of them from this, your language you learn, the learnings you have from your childhood, the culture, your beliefs and experience is a huge. So you have this whole repository of database in your own head. So then you have a conscious memory, which is an active memory. Then you have imaginations and dreams. All these things are not static at all. They're dynamic. So as these guys are dynamic, that means the neuronal networks are constantly getting not totally revived, but they are modifying. And the scientific evidence says if we can practice, you can actually train these networks to your advantage. Something like habit. For example, somebody is a chain smoker, they give up smoking and they pick up something else, they're shifting their attitude. Similarly, somebody likes, like Nissa making carbon fibers, if I can convince her biology is good, she may change to biology, right? So what that means? It's basically retraining these habitual processes. They call choose to change your mind. So yes, I think, but I don't want to stretch here too much and say everything is possible. No, all I'm saying is, if you think it is not possible to change, answer is no, it is possible to change. But you say, I change 100%, I don't know. It's like somebody challenges me here, can you be totally like Dr. Chandra's brain? Probably not. It's difficult, right? And of course, he doesn't want that also. So. And then I used to, in my lectures, I used to say if there is a head transplantation, would there be any real change? Is that going to be? But now I understood a little more, is head is only a part of our total intelligence and memory. Apparently, is a lot more systems in our body is also playing a role. So while I gave the long answer, direct answer, the question is, can we consider that these neuronal pathways, can they be rewired? Answer is yes. And can they be adjusted? Yes, it can be done. Yeah, but it requires a lot of practice. And some people go for the medication, some people go for certain medical treatments. The others choose meditation, changing the lifestyle.
Thank you, sir. Sir, there is a follow-up question from Mr. Alok. Yes, is it possible to apply non-invasive electrospun fibers for capturing EEG signals? And how difficult it will be, since noise will be a major issue?
Yeah, yes, it is a problem because right now the current EEG instruments are much better. And we have been thinking about it. We still haven't got a good way how to do it. You're right, the noise to signal issue is there. But I encourage you to do this. If you can come up with a wearable cap and which is completely textile, even whether you use electro spinning or not, but if you are able to make those caps other than the standard sensors, I'm very sure you would be able to make it much more sensitive, also much more comfortable to wear. More than that, you can now think of reversing it to modulate the brain waves. We have alpha, beta, gamma, delta waves in our brains. And if there is a way you can actually externally modulate them, I think you are already helping certain people with certain mental difficulties or challenges. Of course, they're not going to be as effective as invasive, because invasive are directly going to the target tissue or the specific region of the brain. But in this case, even though you're not approaching directly into the inside invasively, non-invasively also, you should be able to address some of them. So I've seen some papers published in Nature and Science where there are professors in Canada. They now say they tried on their students, well, agreed students, and after that they became more creative. So I'm thinking, wow, that's very good.
So thank you so much, sir, for your kind replies to the questions. So in the end, on the behalf of Carbon Lab, I wish to thank all the distinguished speakers, Professor Sriram Ramakrishna, Dr. Nissa Saleem, for sparing their precious time to share their research ideas. We believe that all the Carbon Lab members, alumni, and other viewers on YouTube found it very useful and may get some new insights in their areas. For more information to our viewers, we will meet again at the same platform next month on 13th February 2021 with yet another exciting webinar on research development related to the electrochemical sensors. So see you there.
Okay, bye-bye.
So
Thank you.
last but not the least, as a part of the 10th year celebration, we are excited to announce an international SciAT competition being organized by Carbon Lab along with the Indian National Young Academy of Sciences, INYAS, with the support of National Young Academies of Bangladesh, Sri Lanka, and Thailand. SciAT Image Competition is an effort to encourage creativity among young researchers to present their scientific findings in an artistic manner for public outreach. Kindly visit INYA's webpage for more information. The entries for this competition may be submitted from January 22nd till February 5th. You can follow these discussions and the further updates on our official YouTube channel. Take care, goodbye, and stay safe.
Thanks.
All the best. Thank you.
Thank you.
Thank you.
Oh, everybody's still here, so I can't go away. So you stop recording, or still recording?
Madhvi, you can stop the streaming.
Otherwise, you can't hold the smile that long,